Thank you. And we're here to talk about what we've seen emerge in patterns and the lessons we learned with 2 decades of running a single specific production service at Google.
Hi there, yeah. So I'm Murali. For those of you who knew me at Google, I went by Mux. Spent about 10 years there, originally a user of Chubby, the service in question, and in 2018, I became the SRE tech lead for Chubby, which I did for 3 years until I left in 2022 to join Snowflake, who have very generously let me be here today. We are hiring in Dublin even. Come and bother me if you're interested.
And Chubby, the lock service, was my first SRE project at Google. At the time, I was also working on the productionization of our cluster file system, GFS, and this is important, as you'll see throughout this talk. And since then, I've worked on some other applications and also on SRE education stuff. But today, we're going to talk about how we identified some patterns in lock service, and we draw on many interviews with our colleagues who also maintained and wrote the lock service over the years. We're going to start with some background on what the lock service is.
So yeah, what problem were you trying to solve here? The original thing that we needed Chubby, the lock service, for was leader election. So this is the concept of you have many distinct processes. You want one and only one of them to do a thing. Right? We'll talk about what thing that was in a second, but this, it turns out, is a non-trivial problem, right? And in the early 2000s, there were lots of like cluster type things, right? You had an active backup. I'm sure there are many people who can remember like various vendors who sold various like magic 6-figure snake oil clustering things, but it wasn't like a well-understood discipline that you could just go and do yourself. It was quite difficult. And you know, you had to deal with network partitions, you had to deal with machines going away and coming back and all this stuff. And it's like, that is the problem we're trying to solve, is agreeing on a leader under variable levels of certainty. So what was the first thing? The first implementation was basically provide a Unix-like key space, right, /ls, ls for lock service, / a cell name, and then some path to a node, and then lock that file, unlock that file, see if it's locked, and maybe store a little bit of data with it. And the client API was fairly limited and also fairly generic, right? You had open and close, get a file handle, get rid of a file handle. You had acquire exclusive for read locks, read write locks. And you had the ability to set contents and get contents. So small, and we're saying contents, small amounts of data, right? Bytes to kilobytes, not much more. It was intended mostly to store kind of advisory metadata, but as it turns out, you give people a hammer and they will use it for stuff. Additional things that it had, because the person who wrote it thought they would be useful, it had the concept of a watch or notification system, right? So you as a client could say, I am interested in whenever something about this node changes. Please tell me when it changes, right? I don't want to have to come back and poll you. I'll just have a channel open and send me a call back if the holder of this lock change, or I'm waiting on this lock. Just give me a notification. And these are distributed systems, right? It's across machines. So yeah, that's the problem. And then what specific problem were we trying to solve? The problem this was actually built to solve was GFS. So GFS was Google's original cluster file system. There was a paper in 2004, I think, about GFS. This was Salim's first job. How did GFS work? Realized I should have put a diagram here. I didn't. Short version, imagine a cluster of 5,000 to 10,000 machines. All of them have hard drives in them. Every one of those machines approximately runs an FTP or a web server where you can do get file, put file, and then you have one machine in the middle, the leader or whatever, that knows every file that exists on all those machines. And so that thing offers this GFS API, which is like, here's the cluster level file system. And you say, I want to get /GFS / this cell / Mux's MP3s or whatever, right? And the leader then looks in its index and goes, okay, that's stored on these 3 particular machines, on these files, go and get those files. That's how GFS worked. Problems. 2 problems that eventually they ran into. One was availability and one was like scaling. So the scaling thing is less relevant to this talk, but I'll mention it anyway. the leader node had to store in memory information about every chunk on every server. And so the size of the overall cell that you could address was bounded by the amount of RAM in your largest machine, which at this time was 8 to 16 gig, I want to say, ish, right? And so, do some maths and you can work out, and at times, I think 50 meg per file, I forget what the numbers were, but, times that out and it gives you your upper bound on your total addressable storage. The other problem was availability, right? So this name node, in memory serving, goes down, can't read anything, can't write anything. Partitions from the network, can't read anything, can't write anything. Like, it's just complete unavailability. And what was GFS used for? It was the thing that they had downloaded the copy of the internet into. It was also the thing that they saved all of the ad click logs into from which they calculated billing. It was just, that was the thing, right? GFS unavailability became a real problem. And when those machines went away, someone would page Salim, and Salim would desperately try to find a working machine with vaguely current, logs of the state of the GFS cell and try and get it into a leadership. He would null root the old machine at the network layer to make sure if the old leader came back, it didn't start doing corruption things. It was all just kind of a pain. So Google were like, this is expensive and it's not great. Let's hire someone to solve this problem. And they hired a gentleman named Mike Burrows, who we owe huge amounts of thanks to, by the way. He spent a lot of time on this project with us to chronicle its history. And he was told, build leader election for GFS. We want to have replicated GFS leaders, and we want to have cold standbys ready to take over as soon as possible, automated, so that Salim can get some sleep, basically, and Google can keep serving, whatever. So what do we get? We get contents, set contents, and we have lock. The verbs are a bit more detailed than this. That was what we did. And so Chubby, the lock server, is born. You'll hear Chubby and lock server. We would tend to use lock service because the service became more about locking, and then there were other components and whatever. So this is SREcon. The naive implementation is you just put this in memory, right? We have a process, it's a relatively small namespace. We'll just put it all in memory. This is SREcon, so I now need to say something tedious about single points of failure, blah, 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 blah. So, okay, first, let's serialize state to disk, and two, let's make sure that that state is replicated across multiple machines so that, you don't want to just give high availability to the GFS leader and then turn your lock server into a single point of failure. So they went with 5 replicas to start with. They used Paxos, which was a distributed consensus algorithm originally developed by Leslie Lamport to guarantee correctness. Strongly consistent read semantics, and there was a standard client library, right? So you, as a consumer, you link in this client library which knows how to find your local lock service cell, acquire a lock, and so on. It's worth noting the locks in this case were advisory, right? So you as the caller would be like, check for this lock, but it was on you to make sure that you only did dangerous code when holding the lock, right? It was very much advisory. If you did the wrong thing, well, that's on you. But the GFS people were like, we would like to not lose data, thank you. So they, as far as I'm aware, there were never any, oops, I forgot to be holding the lock before I did something dangerous. And so it works well enough, and lots of people use this, right? So we started with leader election, which was, and originally it was for GFS, but it turns out this is just a general useful property when you're building distributed systems in first one cluster and then many clusters. And then people are like, so you're saying we have a thing with keys, and we can put values with those keys, and it's everywhere, and everyone links in this client library because they have to read from GFS anyway. So maybe we could store other stuff here. In the outside world, this would be like JSON. Inside Google, this was serialized protobufs, right? But people would just stash stuff there, and then they would be like, oh, and then I can push my config by just writing this file, and then everyone will get a callback, and I'll synchronously crash all my binaries because I had a corrupt protobuf in my config, and that was great. And then you put name lookups in there. The watch semantics, it turns out, was super useful for service discovery. Excuse me, because you didn't have to care about DNS TTLs anymore, right? If everyone can just watch files in the lock service, when something reschedules under your cluster scheduler, this actually predated Borg, but whatever, or co-evolved with Borg, but your Borg, I don't know what the Kubernetes equivalent of the Borg prime node is, but it reschedules the thing, it updates the file in lock server saying, this is where this task lives. All of the people trying to connect to that task immediately get a notification, they reconnect to the new IP and port. Great success. And then someone was like, security is annoying, and like encoding what principals can talk to what is super, super irritating, and what's a member of what group is really, really, really irritating. How about we just put that as a bunch of files in lock server and have everyone watch them in real time and use them for all their authorization checks? So to recap, we hired a person to solve a specific problem, which was leader election for cluster file systems, and then we accreted all of this stuff over the space of, I want to say, like a year or two.
It was a year.
Right? Yeah. And this was great right up until the lock server started falling over, right? It's like, it's not ideal. So the V1 was very generous as well, right? We're talking very early days of Google. There was no uniform authentication authorization platform, right? Like there was a flag --GFS user, which, yes, a flag in lock server referencing GFS, and this was just a string, and lock server would just believe you. Whatever that string you put in as your client, it would just believe you, and that leads to some interesting challenges for the first Chubby SRE or lock service SRE at Google.
Indeed, and because we would take whatever string was passed in as, hey, I'm the user who's writing data, that would be then attested in lock service as the owner or modifier of the ACL. And remember also, we were just saying that all of the general company-wide ACL information was stored in lock service itself. So we couldn't introduce a circular dependency where the lock service checked that information. Because that would lead to some pretty bad problems if we ever, as a service, had systemic problems. So that is a foreshadowing for some of the patterns of problems that emerged over 2 decades of working with lock service. And although these accreted use cases built up very quickly after lock service was introduced, we found that we encountered some of these issues time and again. And so we're going to first take a look at a few of these patterns, and then tease out some of the lessons that we learned when working with them. And a lot of these will be familiar to you. The notion that we want cattle, not pets, which is to say that we don't want specific special instances of any hardware or software, anything that we need to have a particular one-on-one kind of relationship with. Yet that's almost immediately what we built with the lock server, where we had 5 dedicated pieces of hardware that couldn't be part of the shared fleet in our nascent internal cloud. And while the notion of having 5 dedicated pieces of hardware that are all your own might be kind of thrilling at first, but when it turns out that you have 50 such instances of 5 machines, it's the absolute opposite of thrilling, because then the moment that any one of these has a memory problem, a disk problem, some kind of problem, it becomes an emergency. Because almost every other piece of infrastructure, almost every application at the company was depending in real time on this service. It was depending on real time to do the service discovery, to perform ACL checks, to find pieces of configuration information, all of these built on uses. So we needed to find a way to move from having very special, that's capital V, capital S, pieces of hardware to having things that were more fungible. We also needed to make sure that we didn't introduce additional complexity even as we sought to sort of regularize or normalize the operations of this piece of software. And that is because complexity is often antithetical to having a reliable system. The more you have in terms of the lines of code or different moving parts, the more complex the system is and the less intelligible it can be to someone who comes in to observe it or to work with it. So for example, when we later, or actually very quickly, decided to add proxies to lock service, or later to replace the consensus algorithm that we were using, we needed to be very careful not to introduce complexity and to provide something that was basically a drop-in replacement, so that we didn't do anything that would change the API or cause problems for our users. We also needed to defend against cascading failures. And these are sort of failures where if you have a misbehaving or problematic client or a hardware or software failure in one location, often the traffic that's coming to that location will be automatically sent to a different instance or another machine in that same cluster. But of course, if you have a thundering herd, a bunch of clients all cause one instance of the lock server to fall over, it doesn't help to send all that traffic to just another instance because it's quite likely that will also fall over. And part of what we did to guard against this was to build a proxy because the popularity of the watch interface to Chubby was so great and it resulted in such a lot of read traffic. We thought, great, we'll put a read proxy in front of the core lock service. But that in turn introduced a cascading failure problem for that proxy that we needed to provide some defense in depth for. And now we can take a look at some of the lessons that we learned. And our first lesson was about accountability and isolation. And this is because there's a tragedy of the commons that you risk when there's a single piece of infrastructure where all of your cattle can come and graze. And recall that we were just letting anyone come and say, I'm here, I'm so-and-so, and trust me on this. So we didn't have a way of really truly knowing which callers were overwhelming the system or who was using an outsized quantity of the resources such as memory or the number of RPCs sent at any moment to the system. And we could take a look at this by digging through logs, but that would be almost certainly after the fact, after the horse had gone and the barn door was closed. So what we wanted to do was find a mechanism to provide isolation so that one user wouldn't cause problems, one misbehaving user wouldn't cause problems for another user. We also needed to find a way to provide some sort of enforcement for that isolation. And for a long time, the enforcement was literally a stick that we had. It was a baseball bat that was engraved with Chubby SRE gooning tool. And we took it to, let's say, discussions with developers who were not using Chubby in a polite way. But not only does this not scale, it turns out it's not a very healthy approach to things. So we sought to automate that. And by this time, we had developed a true, very low-level authentication and authorization system. And we built on that to introduce a per method, per client rate limiting system. And this meant that we could say, for any given client, they were limited to a certain number of RPC calls per message if we needed to. And by default, everything was unlimited. But the moment that we needed to make enforcement or to add any kind of rate limiting, we could update a protobuf and send it to the lock service leader, and then the rate limiting would take effect. And this was a much more polite and effective and scalable way of doing things. Our second big lesson was that good API design is priceless. And Murali mentioned that the lock service implemented what at Google was called the file API, which made the interface look very much like a distributed file system. And this was great because it gave developers at Google something that they're immediately familiar with, that they're very comfortable using. And in fact, they found lots of uses that we hadn't anticipated for lock service. And so something that was a convenience for programmers when we were building the lock service also became a very early convenience for people who were using the service. This was great. It did give us a very clear example of what's now known as Hiram's law, which is that all observable behaviors of your system will be depended on by someone. And you can read more in the full text of the law, hiramslaw.com. And this is important because it meant that once we had deployed this, any changes we made to the API, even though there was a very clear API, any changes we made would inevitably affect our users. And some of these users were, again, in real time depending on lock service to make decisions about very business critical things at Google. Our third lesson we'll call first mover disadvantage. And in this sense, lock service was the first mover because it was one of the first pieces of company-wide production infrastructure that we built. And it sat at the very base or foundation of our production infrastructure. Our shared compute depended on it, all the job scheduling. Our shared storage depended on it for leader election and for service discovery. And so in order to prevent lock service from having circular dependencies for storage or scheduling, we needed to bake some of these concepts into the lock service code itself. And this was great because it meant that hermetically the lock service could start from a cold boot, essentially, and then the rest of Google's production environment would, in theory, follow. But what this also meant was that we had a lot of custom code in the core lock server. And this meant that we couldn't do things like adapt to new features in the RPC system that's in common use at Google, and you may know as gRPC. And lock service had an early streaming implementation of RPCs, which was great for things like the watch part of the API. But later, when the RPC infrastructure added its own streaming interface, we couldn't actually move to and take advantage of its increased efficiency and more widespread adoption. Similarly, we couldn't use features for distributed tracing that were, in theory, a system-wide tracing tool. But it wouldn't work with lock service because the way the annotations were set up relied on libraries that we couldn't, again, for reasons of circular dependency, we couldn't include in lock service. And it took a few years of pretty intense refactoring in lock service to get to the point where we could start using the tracing tools. And that then brought us to a better place for understanding, hey, who's calling lock service, who's placing an outsized load on us, who's doing weird pathological things with us. And our fourth big lesson was about the value of iteration. And early on in, even though we're talking about 20 years of this lock service, the first year was almost like a big bang of exploding use cases and very exciting changes. And one of those exciting changes was that we identified the need for a read cache. And we built this read cache and rolled it out, I think, fairly successfully and fairly quickly. And it addressed a lot of big issues with load and a popular use case for some very critical Google services. And so we'll give that a green check mark. That was a successful iteration. And then the next big iteration was the addition of a write-through proxy. And this was, it took a lot longer, several years, to get to the point where we could build this and roll this out and really understand how it would work. Again, we were seeking to minimize any additional complexity that we added to the system. So we maintained the same API. So this was an almost transparent change to users. And we rolled it out. It was hidden behind or guarded with a flag change. And pretty much all users were okay with it. There were a few users who still needed to speak to lock service directly, and we worked with them to understand what their concerns were and eventually move them to talking to one or the other of the proxies. So we'll give that one a green check as well. And at this point, we're several years into running lock service as a production service. We've got SLOs. We understand what our users are expecting from us. We have a really, I think, a decent level of we have a decent number of nines, I can put it that way. So we thought, all right, we can rest on our laurels, or we can try and bring new features to our users. So we decided that we're going to build a parallel lock service deployment. And at this point, you might be thinking, all right, this is interesting. It gets a little better because this parallel deployment involves an API change. And the idea was we'd give users who wanted really, really strong guarantees about data durability, we'd give them the opportunity to write to this, to both the primary and then a parallel instance of Chubby, of lock service in the same data center. And they could do this so that if there is some previously unexposed bug or systemic problem in lock service, there's a parallel system that's running a build that's 6 months out of date, and surely that wouldn't have the same bug as the first one, right? So we introduced this to clients who wanted even stronger guarantees, and they went through the fairly time-consuming process of updating their API calls to lock service. And then we found out that it didn't really matter. It didn't matter because clients didn't actually want to use it. It introduced latency in their calls because now they're making 2 calls to lock service in order to find the leader for a cell or to go through a round of election. It introduced a lot of toil for the SRE team because it meant that we now had twice the number of very special servers running in production. And remember also that there was that first mover disadvantage, which meant that we couldn't use many of the common tooling across Google for things like rollouts. So we had already built our own rollout system. We now had to adapt that rollout system to understand that there were 2 parallel instances of lock service, and it did not end especially gracefully, which is why it gets that red mark on the screen. And we turned it down after about a year, a little over a year. And the lesson here is that sometimes iterations are not fruitful, and you may develop a feature intended for reliability, and then it doesn't actually do you or your users any good, and it's okay to remove that feature. So where do we go from here?
Oh no, this is you.
There's a long-standing in-joke among Google engineers that says, is Chubby a file system? And there's a single-serving website internally that produces this graphic exactly, which is, the answer is no, it is not a file system, even though we've been going on about how it implements a file API. But
yeah, I mean, and this I think is one of the really interesting things kind of generationally, right? So for people like Salim and a few of the other future hecklers in the audience, I suspect the answer to this question is no. Someone who joined later is like, the team I was on before lock service, we stashed all of our config in lock service, right? Like we absolutely were treating this as a file system. Like it doesn't really matter what you build it for, it matters what you let people use it for. And I'm sorry, I know that you think you're in the business of distributed consensus and locking and leader election, but if you let people put pipes in and then get them back later, you are responsible for their data and you are running a storage system. I'm sorry if that makes you sad. So yeah, in terms of what's next, there were kind of, so I joined in 2018, late 2017, early 2018, and the challenges that we were running into with lock service at that time mostly had to do with all of the things Salim mentioned about both first mover disadvantage and like just explosive adoption of this very, very generic, easily composable API, right? If you think back to all of the use cases we talked about, you had, so what did we start? We started with leader election, right? Leader election is like locking leader election, you can treat them approximately the same thing, right? It's like acquire lock, release lock, check who has lock. You want it to be fast, you want it to be correct. You probably don't need durability, right? Like you can imagine an implementation where the lock server gives you a lease, right? You're like, you have this lock for the next 50 milliseconds, and assuming you have reliable time synchronization, and there is a current lock service SRE whose problem is time somewhere in the room. But assuming you have that, you can do a very, very simple thing that doesn't need all of this distributed storage, right? You contrast that with, say, the ACL use case, right? Or the config use case. The config use case is like, this config is super important, right? This config tells me which data centers should or shouldn't be receiving traffic right now. That needs to be correct, it never needs to be corrupted, it needs to be readable by clients who need to check on things. The ACL use case, that's security sensitive, right? That puts you inside the boundary for whatever compliance regimes you're a part of, right? In the days before universal authentication authorization and kind of user-specified encryption keys, Salim or I could just add our names to the end of one of those files and it's like, hooray, I am now like whatever, right? Like there's just a bunch of systemic things which weren't really considered early on. The service discovery use case, they don't care about durability at all, right? Like if we accidentally blew away / Borg naming under a given Chubby cell, like Borg SRE would be a little bit grumpy with us, but their software would rewrite all the records and it would be fine. And all of the read and write workloads for all of these things were just vastly, vastly different, and they were all being served by the same serving infrastructure. And so it made it very difficult for, and more importantly, being served by the same serving infrastructure and using the same client API, right? Like, there was conceptually in the code, you just had file paths and their contents, but to work out that this was a watch for a service discovery request, you had to look at the name of the file, right? It was opaque to the service, and you had to match on that, and you had to know files under this path. Oh, that's under /borg/bns/whatever. That's a BNS thing. The durability matters less. Like, there's no way you can feasibly engineer for that. And so the things that we needed to bolt in later were, first, user isolation quota management, Salim already touched on. Putting them enough to the fact is so, so difficult, right? If you're going to build a multi-tenant system, and maybe most people probably aren't going to do that these days, right? Maybe you outsource that to Kubernetes or your cloud provider. But if you're going to build a multi-tenant system, build your quota enforcement in early and actually enforce quotas from day zero so that customers know there's a quota somewhere, right? Don't let them do whatever, and then 5 years down the line, you suddenly have everyone fighting over what is now a contended resource. Those conversations are super annoying. The observability piece is also really difficult, right? To the point about everything is just a file open, a file read, or acquire lock, release lock. We needed to build all of this telemetry to then work out what the hell people were using this thing for. And we basically just dumped it all into BigQuery effectively. And then we wrote queries where we were doing string matching on the keys. And it's like, okay, this set of clients is caring about this set of files. Maybe we can talk to them about, hey, is this a use case that you actually care about, right? But it was not something we could do in the serving path. We could only do it with rich semantic knowledge of what our users were using the thing for, which is not where you want to be as someone who runs a storage system, right? The data is yours. We just run the infrastructure. And then that leads to kind of the iterative design piece. The file API gave us rapid adoption and great flexibility and really good ease of use, but it made it very hard to deliver these distinctive use cases and implementation. So one of the things we started doing was we would look at use cases and go, okay, locking. You know what? This is a well-defined constrained problem. We're just going to create a new lock API. And from day zero, I think to start with, we backed it by lock service files. And then later we replaced, and that was a client library change. So we migrated everyone to a new locking API, still backed by lock service. And then later we flipped the default, or planned to flip the default to a new implementation that was in-memory only locking, right? Similarly for config push, right? We built high-level config push systems originally atop lock service, later atop other systems. Service discovery, right? Like talking to the Borg people about, hey, let's build dedicated infrastructure just for naming and service discovery. And so all of these things become their own APIs, which could then be pivoted to be served from different infrastructure, which could be optimized for each of those use cases. And I really struggle with this because on some level, you don't know what people will need. It's hard to know what people will need ahead of time, right? The fact that this file API was just generic and useful is what let people build all these useful things. But possibly we, lock service team, left it too late to become opinionated about, hey, okay, a lot in 2010, if we'd said, a lot of people use this for locking and leader election, we should make that its own API and say from now on, if you're doing locking and leader election, use this API target, not the generic file one. It would have made my life in 2018 a lot easier, right? But it's just hard to know that at the time when you're in the middle of things. So yeah, there's still a team. There's a bunch of people in Google in Dublin who work on this thing, and they're still working on it. They're still improving it, and hopefully things are marginally easier and more manageable for them now. Big thanks we really need to throw out to is Mike Burrows. As I say, he's original author of Lock Service, right? Also the paper that was published in 2003, 2004, and he spent several hours. Also, he was just generally helpful, right? We would turn up in California and say, "Hey, do you want to talk about Lock Service for a while?" And he would, because he has nothing better to do. And he also spent a lot of time with Salim and I. We just interviewed him and chatted to him about, what were we trying to do. And then there were a bunch of other colleagues. We interviewed a bunch of other people about the intervening history, and then specifically Dan Ludke and Todd Underwood reviewed this presentation and gave us a lot of useful feedback. And Christine Chen, I think, as well, did a review. I may have made it. Anyway, there was many, many people. So it wasn't just us, is the thing we wanted to say. So that's what we got.